Thanks for joining, everyone. This is our EMA seminar series. So we try every few weeks to come on board and give you some information on general topics with respect to electromagnetics for aerospace applications. Bryon Neufeld, PhD, is going to be presenting some details of ways you can model spacecraft and their plasma interactions, and then some of the EMC, ESD problems that occur from those interactions, how to accurately model that. So as we go along, if you have questions, please type them in the Q&A box, and we will answer them at the end or as we go. Thanks again for joining. Let us know afterwards how things went and any new topics you want us to cover in the next session. So with that, I'm going to turn everything over to Bryon Neufeld.
Thank you, Tim. Okay, so hopefully we'll have an interesting presentation for you today. To get it started, we'll introduce just a little bit of the context. So what do we mean by space plasma discharges, and what is the problem we're attempting to model? So we're in the context of electrical discharges that occur due to surface charging caused by space plasma. There could be differential charging that builds up between surfaces on the vehicle or between a surface and the vehicle ground. There could be absolute charging that builds up between the vehicle and the plasma. And there's also a possibility of what we might refer to as a rendezvous type discharge, in which two docking spacecraft experience a discharge. And so what we're going to analyze here, we're going to focus on the rendezvous type discharge and the discharge to plasma. And the technique we show would easily be extendable to the differential charging as well. So a little bit about why I use this tool, EMA3D, for this particular problem. Well, in our mind, or in our opinion, we think that EMA3D provides a strong single framework through which you can evaluate space discharge transients, but you're also using a tool that involves a full solution of Maxwell's equations and is very well suited to other EMC type problems. EMA3D has got a great validation heritage. So you're getting a single, from a single geometric model, you're getting a whole host of EMC problems you can attack. It's just a comprehensive E3 simulation platform. And in fact, during our demonstration in a minute, we'll show how essentially we use the same geometry 3 different times in 3 different ways to analyze this notional platform. Okay, so one more intro slide before jumping in. So this is our, this matrix here shows our recipe, if you will, for how we approach this problem. So as with basically any problem, you start with the geometry, and the EMA3D and CAD-Fix platform supports native imports of CAD, and it also supports state-of-the-art CAE development. So you can natively import CAD for your model. You can develop it using all kinds of advanced techniques to make the model have good fidelity with the physical properties in the model. And then also there's great mesh control in this approach. So within this platform, we have the ability to take the same geometry and make a finite element mesh, which will be used in surface charging, or a tartan mesh for the finite difference time domain solution. And the user controls that from the resolution and the algorithms and all kinds of aspects, and you can have the same model, different meshes, and different solution, different problems you're looking at. Okay, and then the material assignment is controlled, and that can include materials for both the surface charging and the finite difference time domain solution. And so the way the recipe works, once we get the model together, is that we interface directly with NASCAP-2K for the surface charging. The surface charging allows us to evaluate the voltage on the vehicle. The next step is, for the given system of interest, we'll evaluate the capacitance using EMA3D. This gives us the total charge expected from the discharge waveform. So you have a voltage from the surface charging, and then a capacitance just from the geometry using EMA3D. And then that allows you to constrain or normalize the total charge in the discharge waveform. And then once we have that total charge, we have completely determined the discharge waveform, and we can now go to the discharge transient analysis. So we'll show in particular from EMA3D our SEAM algorithm and M-harness. But it's a very simple model, and we want to emphasize that what we show today can be easily extended to real, fully detailed models and complicated vehicle platforms. We'll also show how we can couple the energy from the discharge to antennas. EMA3D has some built-in capabilities that allow one to couple, for instance, from the full model analysis and then evaluate around a box around an antenna, and then run a second model that has a finer distance resolution where you could analyze an antenna directly. Or we also interface with external formats, including EMScan. And then you can take this model and go on to your other E3 challenges. So now we'll move to video portion. And we have 3 short videos that demonstrate these different approaches, and they're not terribly long, so we'll show a short video and then some results. Okay, so as we said in our recipe, the first part will be to obtain some surface charging results, which gives us a voltage. And this is the model we're going to be using. We'll call this the capsule. And this will be, this model is going to serve as the basis of our surface charging, and we'll also then use it later for some of the discharge analysis. So we've imported this model from native CAD found on an open source website, and then we've just imported it. You can see in our platform here that the user has all kinds of options for native CAD import. Now what we've also done, we mentioned we interface with NASCAP-2K. So we've imported this model, and maybe you have done some work on the model once you imported it, and then you're ready now to start thinking about the surface charging. If you're using NASCAP-2K, we have some tools. You can see the GUI buttons here on the side. And so first you can assign your NASCAP material property, and then you can assign it to regions of the vehicle once you've defined the property. And those materials carry over into the surface charging simulation. The user then also has the opportunity to control their finite element mesh. So, for instance, this mesh manager allows the user to look at different algorithms for the mesh. You can have different algorithms and different resolutions on different parts of the vehicle. There's just a lot of control over that. There's also a built-in option that we have for the user. So if you don't want to mess with controlling the mesh carefully, you can just put in some basic number, which is a single number for the resolution. Now in this particular case, we have already meshed this model, as you can see. So once the model's already meshed, the user can export it with our Advanced button. And then it exports as a NASCAP object for simulation. And so this is the model as it directly opens in the NASCAP 2K Object Toolkit. You can see that the mesh and the materials have carried over. And then what we've done before the webinar today, we've simulated this object in an arbitrary space environment to get some voltages on the vehicle with respect to the plasma. And that's what we show here. And what's interesting here is that we're going to be looking for areas that, for one thing, we'll want to know the voltage on the vehicle chassis with respect to the plasma, and that's shown to be about 4,000 volts, and that'll be useful for the docking problem. And we can also take note of the voltage, for instance, on the highest area there where the window is. So we'll use these voltages to help constrain our discharge waveform. This will help constrain the magnitude of the charge in the discharge. Okay. Okay, so now we're ready to start looking at results. So we'll go to the next slide. Okay, so once we have the surface charging done, this is our waveform for the discharge. This is a fast double exponential waveform. This is a waveform found in the NASA handbook. But what we have to use is the voltage from the surface charging helps us constrain the magnitude of this discharge waveform. And so we already have the voltage. And then what we need next would be the capacitance of the system. And so what we're going to do now is we're going to go back to this capsule model, and we're going to consider a docking problem first. We're assuming that, so the other part of our model we're calling the space station, and we're going to assume that that's at about minus 20 volts with respect to the plasma. And so we'll show this geometry, and we will go through the steps of how we constrain the capacitance and the discharge. And then we'll show a transients at the pin level and show how you can evaluate the potential risk of discharges. Now, one thing before we enter into the next video is we'll point out that when we route cables and talk about transients at the pin level, we're referring to taking advantage of M-harness, which co-simulates with EMA3D and allows you to model a microscopic description of a cable harness. So it includes an overshield, it includes inner conductors, and it allows you to evaluate how cables interface with electronics boxes. And in our model, we have a couple twisted shielded pairs that have been routed, and we'll show the transients on the inner cables as well as the shields. And we also take advantage of EMA3D's theme algorithm, which we'll be showing in the demo, but just to point out that this theme algorithm allows you to model themes and allows you to faithfully control how energy couples inside the vehicle. And we'll be modeling conductive vehicles that only have openings through the seams. So in our problem, the seams really control how all of the energy couples inside. Okay, so we're now ready to look at the docking problem. What I've got shown here is the model for our what we'll call the rendezvous or docking. Now, this is the capsule model on the left is the same geometry we use for the surface charging. And what we've done is we've imported a second vehicle, which we call the space station, and they are in the process of docking here. And we're showing the tartan mesh. So before we had shown a finite element mesh, which was for the surface charging. Now we show the tartan mesh, which will be used for the discharge problem. Now we have a voltage difference between these two vehicles, which we know. We said that the surface charging had some voltage on the capsule, and we assumed some voltage on the space station, which we'll call it. But now we'll want to have vehicle capacitance, and so EMA3D allows you to do that easily. So you can take a known waveform and evaluate the voltage difference between the two vehicles. So for instance, the EMA3D has a voltage probe we can use. And we can put points on each of the vehicles. Since they're PEC, should be equipotential, so it's a pretty robust way to get the voltage difference. And we just have some known waveform. So it's not the discharge waveform we're going to look at in a minute. It's just a test waveform where the voltage is already known. You can see what this probe looks like in our emin file. This is the file that's used for this first simulation. And this on the left is the output of the voltage. And so you can see the voltage starts to saturate as a function of time there. And we can pull off that number. I just cut it off where I thought it was reasonable and use that number. So that voltage along with the test waveform charge gives us the capacitance. So now we have been able to constrain our discharge waveform. So the blue line here shows where we've assumed the discharge will occur between the vehicles. Now we've also routed, as I mentioned, a couple simple wires in here using M-harness. And we've also included some seams. So first, these are the two wires that are for the M-harness routing, a couple twisted shielded pair, about 20 gauge wires. And they go right around these blue lines, which are the seams. And so what we'll do is we'll have the energy from the discharge will couple primarily through the seams to these cables. And we'll look at the results of that. As I mentioned, the vehicle is just PEC, so all of the energy will couple through the seams in this case. Okay. And we're just showing a few more angles of the seams here. Now, as we mentioned, the seams are an important part of this particular problem. And so within EMA3D, you can define the seam, and that's what we're showing here on the video. And you can control the resistance, inductance, and capacitance across that seam. So that provides the user with a lot of ability to control this problem. Okay, so now that we've shown the problem, here are what the results are. So we define the problem, we've got our seams, we've got our M-harness cables, and we've got the rest of the body is just a perfect conductor. And so we ran the simulation using our discharge transient waveform, coupling across that blue line we showed. And here's the results. So we're plotting results on both the overshield, which is the upper left plot, and then in the lower right plot we have the SAG1 cable, which is the inner conductor. And this is a very fast waveform, as we mentioned, so the double exponential is very fast. So most of the actions occurring there in the first about a tenth of a microsecond or so, and that's where we cut this off. But you can see, and depending on the geometry, the coupling might look a lot different. This is just our particular case. We also look at the other segment, which was, this was the segment inside of the capsule, and it has a kind of a similar structure, and it, again, will depend a bit on how the geometry is, but you see a lot of the capability is there, though, to really analyze this problem. Okay, so now we'll consider a discharge to space. So we just looked at the rendezvous type discharge, and now we'll look at the discharge to space. And in this problem, we're going to again evaluate transients to a cable, but we're also going to look at coupling to an antenna. And so in this case, we could evaluate the capacitance of the system with respect to infinity, since it's just going to be the capsule. And then we can do the same type of analysis and look at the results. Okay, so we again go back to our model. This is the same capsule that we started with for the surface charging and used for the discharge, the rendezvous discharge. So now we're going to be looking at a discharge towards space. Now we already have the voltage, and that was from the surface charging evaluation. We could evaluate the capacitance. We're not going to show that again this time. But we have a discharge to space shown from the blue line. That was where we had the highest voltage from our surface charging calculation, so that's where we would expect most likely discharge to space. In reality, this line goes all the way to the problem boundary, but we just have a truncated line here for the visualization. And we also have, so we have the M-harness cables routed as seen, just right inside, and this other blue line, the circular blue line, is our seam. And so there's going to be a discharge to space. In this case, it's coupling through the seam near the M-harness, the black M-harness lines that were shown there. And we also have an antenna here. So it's a patch-type antenna shown in blue. And we're going to evaluate the coupling to that antenna. So there are abilities within EMA3D to evaluate the energy going into that area where we have our antenna defined. So for instance, our box-in probe allows the user to run this full-scale model and get the energy entering into a region around that antenna, and then run a secondary, smaller microscopic model that has a detailed antenna model. Excuse me. And we also have the ability to interface with EM scan, which allows the user to couple this solution to other platforms that use the EM scan format. Okay, so let's see. Okay, now we're ready to look at the results here. So what we've shown again, we've shown the coupling now. So this was the same discharge waveform, but now we're going to space. So there's a different magnitude and normalization of that waveform. And you're seeing now, again, the overshield and cable coupling that come to those black M-harness cables that are right inside, just inside of the seam there. And the discharge was on the blue line. And it's a similar type waveform as was seen for the other one, although some of the details are different. Now what's interesting is we show some of the coupling to the antenna. We're just showing here the magnetic and electric fields that are entering into the surface there. And so you can see in the upper left we've plotted the electric field, all three components of that. And in the lower right we've plotted the magnetic field, all three components. And it's really that first about 0.04 microseconds or so that you're getting the transient coupling there. And then you can see in the electric field plot that there's a static field that starts to develop, and which is not really, that's not the physical part of the problem. That develops because we've done a discharge directly from the vehicle without it having a certain net charge on it. But you could also run this problem where you first deposit a certain amount of charge on it and then wait some time and then discharge it, and you wouldn't get those static fields, but the first part of this plot would look the same. So that's really the physics we're looking at here. Okay, so what is our summary? Well, we hope we've shown in this short presentation that EMA3D provides a single framework for a comprehensive E3 analysis program. We've shown it in some specific problems related to space discharge transients, but this is a full wave solver that's suitable for all kinds of difficult problems. We've used a single geometric model and done several different types of problems, including surface charging and discharge problems, as well as evaluating the capacitance of a system. And we didn't show it directly here, but we can extend this to surface-to-surface discharges as well. And that's the end of our the content part of our webinar. And we thank you for your time. And there's going to be the opportunity, you've had the opportunity to submit questions, and I believe there's going to be a form that comes at the end as well. And you have our email addresses, so you can either submit questions now or there's options after the webinar as well.
Okay, so we'll start with some of the questions. One is, what's the distance you assumed between the charge structures for the capacitance measurement?
The distance assumed between them?
Yes, that's right.
You know, I think it was about 6 inches. I didn't keep real careful track of that just because we were focused more on the qualitative features, but it was about 6 inches between them.
The next question is what the environment is. Is it LEO or something else?
For this case, we used a geo environment. But it would be extendable to really any environment where you can get the voltages on the system.
The next question pertains to the verification of the approach. So I think probably that has to be broken up into the different sections. So for example, the verification of coupling, that would be probably obtained with a lot of the space vehicle and aircraft validations, which I guess was the subject of a couple webinars ago, but in terms of our seam coupling model, there's quite a bit of heritage and validation that coupling is correct. I guess the other part of the validation is validation of the NASCAP itself, which, as I understand, there is some existing validation work there. And then the last little bit may be what's the validation that discharge is the discharge you get, and so that's the point where I believe your model is empirical. So that would certainly depend on how good that empirical model is. Do you have any other comments on verification or discussion there, Bryon?
No, I think that was a pretty good synopsis of that, Tim.
The next question asks, what happens if your cable you're coupling to is shielded with inner twisted pairs, and how do you do the conversion from common mode to differential mode. So toward that point, if we know the load impedances, we can actually put an arbitrary RLC or combination circuit on the loads, and so mHarness can actually directly calculate the differential mode voltage. So that's one approach. Another approach is to simply obtain the worst case short circuit current and then the worst case open circuit voltage, and then use those as a metric for Mill Standard 461 or DL160 style pin testing. So I think that open circuit, short circuit approach is worst case and conforms with typical EMC testing just because you can be agnostic about the load. But if one wants to simulate directly, that is an option with mHarness. The next question, Bryon, maybe you can answer is how is the shield modeled for your cable?
How is the shield modeled? Well, it's we have so in the EMA3D mHarness tool, there's a great database of modeling for how shields, depending on their gauge, the properties including resistance and radius and transfer impedance. And so I've just used our mHarness tool to model. As I said, it was about a 20 gauge shield with an inner twisted shielded pair inside. So I've just used our built-in database of wire properties. And if you want more details, we could possibly share that via email. But that's one of the great advantages of mHarness is that there's a lot of EMA experience that's gone into calibrating how the shields and how the inner conductors should be modeled. And so there's a great tool that walks you right through that.
So the next question points out that often the discharge you worry about is not discharge to space, but surface-to-surface discharge, which I think is not the point of this presentation, but it's a related and very important one. So they ask, using the tools, how do you find the maximum differential voltage between surfaces?
Well, we have processing tools that allow the user to once they've done the surface charging in ASCAP 2K, we have processing tools that will allow the user to process the results and parse them down according to materials, and it actually prints out the differential voltages across different materials on the vehicle. So the user can use that tool to figure out where the maximum differential voltage between, say, some dielectric and conductor is. And then once they've done that and they've constrained the waveform, they can just basically repeat the same steps they've seen here today and evaluate that type of discharge. There might be a little more complication regarding modeling the current density source line between the surfaces, but that's just a modeling trick. That's there's no real impedance to doing the same problem again. So we believe we have the capabilities for the user to model that problem without much more involved than what we've seen today.
So the next question talks about the charging difference between composites versus metals. And I think most graphite-based composites tend to be static dissipative materials. So I would think that the charging threat of composite versus metal is probably similar. If it's like a glass fiber or something that's more resistive, then I think there's probably quite a bit more potential for voltages to build up. We have several questions related to the fact that in the discharge itself, it's limited by space charge, and certainly that point of the discharge, which you've sized using the total charge available for the discharge, and then use the empirical waveforms. There's a lot of questions about why those waveforms and whether we could do the particle tracking type model. So the answer to that is there are some particle tracking features built into EMA3D, but they're not well validated for the particular space plasma environment. So we tend to use the empirical waveforms that are known for those type of discharges. But that's something that could, in principle, could be done, and with some careful validation work, one could start to think about doing some of the nonlinear modeling. But there are also dedicated plasma tools for particle tracking that may be another alternative compared to EMA3D, where mostly it's an EM solver. Okay, it says, here's a question about how much of this can you do without NASCAP 2K. And so that's certainly pertinent for users outside of the U.S., because you have to be U.S. citizen to use NASCAP 2K without maybe some special agreement. So do you have any comments on that, Bryon?
Yeah, and so it is true that our special tools are designed for NASCAP 2K as far as transferring that geometry and maybe some of the processing aspects. But I would point out that really the finite element mesh information is still obtainable from our platform. So you can still develop that model, and you can actually still define materials. And we could work with a user to try and help them format the particular mesh outputs that might be more tailored for a different surface charging software. But I wouldn't let that be a showstopper, because that's not really a major obstacle in the whole part of this analysis. That's something that we could tailor for an individual user if there was interest.
So the next question is how to deal with ground bounce on the vehicle voltage reference and the common mode consequences. I think, tell me if I'm wrong, Bryon, but I think you can capture the voltage everywhere with voltage probes for the equipment boxes that are chassis referenced, and so you could see exactly what the voltage is, and then use that on the DL160 style kind of ground injection test to determine that waveform. Do you have any comments about that, Bryon, or do you think what I said is correct?
I think what you said is correct.
Okay, so the next question is, does the M-harness shield model also address transfer admittance? So the answer is yes. So the M-harness, we can put in an empirical transfer function for the cable at various frequencies. So that's another place in this model that's empirical. There are models for determining the transfer function or transfer impedance of cables, but we find it's much easier to just quickly characterize that in the lab. And I should point out EMA3D actually has some built-in typical transfer resistance, transfer impedance data for cables. If you're using maybe standard 10 copper over braid, you can just use those directly in the software, and if you've measured your cables, you can put them in a custom way. And then the next question is about why we use the assumed empirical transient versus the real value. I think the answer is just that the modeling simplicity, so that we don't have to use particle tracking or some other type of plasma simulation at that point. Okay, so we have another question just to re-summarize how you did the capacitance assessment for the Rendezvous case.
Okay. Yeah, that's actually a pretty simple analysis. So we've taken we have a known waveform, and it's not the discharge waveform, but it's just some known waveform where the charge is completely known, and we've deposited that charge on the system. and then used EMA3D to evaluate the voltage difference between these two PEC vehicles. And then once we have the total charge on the system and the voltage between the two, then we can evaluate the capacitance between just using a simple algebraic equation.
Okay, so the next question, what models and tools are used to compute the space plasma environments and the dynamic charging? So I think the answer to that is Neufeld.
Yeah.
Let's see. So next question is, what about field enhancements for non-flat surfaces? So EMA3D does take that into account, so we can use EMA3D as a quasi-static E-field solver, and so we can find if something's charged and it's next to another object, we can see how the shape of that object enhances E-field near the sharp points, and that's a common way we use EMA3D. So the next question is about a discharge event from a punch-through. So I think the technical approach could be, one approach could be to do the same thing Bryon has done, but you would just put the source waveform in a different place, and you would use a waveform associated with a punch-through breakdown of the dielectric. Oh, here's a question. What's the approximate number of surface mesh elements for the capacitance simulation? So that would be your FDTD mesh, Bryon. Let's see. So that's not really a surface mesh. It's an FDTD mesh. So maybe you could just tell us your cell size and your approximate number of cells in XYZ.
Yeah, I used a 3-inch mesh for the finite difference time domain, and it's probably about it may have been on the order of 800 cells total for the whole problem space.
Yeah, and I would just point out that that's certainly reasonable for a demonstration, but space vehicles like that, we can do them down to ½ an inch, I think would be typical for that type of vehicle if we needed more geometric resolution.
Absolutely.
Okay, here's a question. Can we distinguish between what we mean different between the surface charge and the discharge?
Okay, so as I understand this question, so the surface charge would refer to a certain buildup of electric charge on surfaces due to their interaction in the space plasma. And so the vehicle would develop some charge distribution based on that, and that's what the NASCAP-2K simulation is analyzing. Now, we only showed voltages on the NASCAP-2K output, but you could also look at this problem and you would see things like electric fields on the surfaces, and you might even see the current flow depending on the problem, things like that. But we have just looked at the voltages, and those voltages are due to surface charge, just a charge distribution, a static charge distribution on the vehicle due to a space plasma environment. The discharge is how that charge leaves the vehicle either to go to space, out into the space plasma, or to another vehicle, or in some cases, if there's a surface-to-surface discharge, you might be looking at how it redistributes along the vehicle. So there's a whole lot of different subtleties involved, but basically you're looking at how the charge that gets on the vehicle redistributes itself to find a better equilibrium, and that's the discharge event.
So the next question is, for the Rendezvous, can we introduce an impedance between the two vehicle grounds? So I think what this would be, if I were to put on my designer hat, maybe one thing you would want to do is provide some electrical isolation between the docking system on a spacecraft, and so by providing some special isolation, you can limit the current, but also make sure you don't build up the voltages. I think that's the essence of the question. The answer is yes. You can certainly, in order to do that internal modeling well, you have to include via seams or the resistance of all materials, the exact resistance between them. So if we designed in special isolation, say a mega ohm isolation, we could certainly put that in directly into the model and capture those design tricks. So the next question is, can EMA3D simulate the surface charge by space plasma? The answer to that is no. We use, for the plasma interaction, the surface charge, we're using NASCAP for that particular case. And then next question is my discussion about Rendezvous and introducing isolation. The question is, in EMA3D, was I talking about EMA3D? And the answer is yes, I am talking about EMA3D. We have another comment. Someone has further questions that they want to get in touch by email. That's great. You can see both Bryon and my email there. We can keep this conversation going. I've tried to give a quick answer to all the questions that came in. I hope I haven't missed anything, but if I did, please email us. We can set up a time to do an individual WebEx, or we can talk on the phone. And take care of anything else that there is. Thanks a lot for your attention. Please also let us know what topics you want us to address on future webinars, or let us know if you have any questions about EMA3D or CADFix or anything else Bryan's talked about. So thanks a lot, everyone, for your time. We'll follow up also with each of you and give you this video and a link to where this is going to be posted on the website. So thanks again, and keep your eyes on your inbox for the next webinar if you're interested.
Thanks, everybody.